Hi and welcome back. This is video 2 of 2 on Chapter 16. Now, Chapter 16 serves to introduce us to the concept of electromagnetic radiation and light as electromagnetic radiation. In the first chapter, or in the first video rather, we spent a good deal of time talking about the fact that light is an electromagnetic wave. We talked about the properties of the electric and the magnetic field and the relationship between the two. And then we talked about the energy that's trapped within light itself. Today, what I'd like to do is to finish up our discussion about light as an EM wave by talking about something called radiation pressure. Now, radiation pressure actually is a pretty big deal. Um, if you consider two idealized types of materials, and I'm going to write them over here. One idealized material would be something that we've actually heard a little bit about when we talked about thermodynamics, and that's a black body. Um, in general, when it comes to seeing things, either you see light that is emitted directly by the object that you're looking at, or you see light that is reflected or scattered off of that object. And in each situation, it conveys information about what the thing looks like. Black bodies are special types of things that absorb all of the radiation that fall onto them. So they absorb 100% of the electromagnetic radiation that falls onto them. Now, if they did not emit radiation, then they would look absolutely black. And that's because black absorbs light that falls onto it. A good example of a black body would be a star. You can create theoretical black bodies in labs that are close to 100% absorbers. And one of the interesting properties about black bodies that we're not going to get into is that when they do in fact emit radiation, they emit it all across the electromagnetic spectrum. Now, the other type of idealized material or object that we're going to talk about is a perfect reflector. Now, perhaps things made out of neutronium might be perfect reflectors. There are no 100% perfect reflectors that work all across the electromagnetic spectrum. For example, even the best mirrors that we're able to create in the labs do not reflect X-rays. X-rays pass straight through them. So you can model something as being a perfect reflector with the acknowledgement that the result that you get is going to be a little bit of an overestimate as to behavior. But nonetheless, it's a good starting point and makes things tractable. A perfect reflector, instead of absorbing 100% of the light that falls onto it, would reflect. Now, that said, what I'd like to do is to consider the situation where you have a ray of light come in and it hits a black body, something that absorbs all of the energy that the light is carrying within it. So, to draw some vectors to sort of give us a sense as to the direction of things here, this right here, when our ray of light hits our object, is going to be the direction of travel. And we know that there's a relationship between the direction of the electromagnetic field, or the electric field rather, and the direction of the magnetic field, such that the cross product between E and B gives you the direction of S, or the direction that the light travels, or K, the wave number. So here at the interface, where light is hitting this black body, you have maybe the electric field that points up like this, and perhaps the magnetic field that points off like that. And this is in fact, a standard right-handed coordinate system. We're going to call this direction here Z. That makes this one Y and this one right here X. And like I said, maybe this right here is the electric field part, and then going out sort of towards us out of the screen would be the magnetic field part. And this right here would be K, our wave number. Now, so that said, if you think about objects themselves, especially solids, they hold their shape because the atoms and molecules on the inside are sort of constrained to live within their own little bonds next to their neighbors. And that's the definition of a solid. It holds its shape. So if you think of this as a solid, when this light ray comes in, the nuclei, which is what we think of as the actual atoms or molecules, those are the things that are sort of locked in place. But the electrons themselves, which have masses that are far, far, far less than that of the nucleus, are the ones that are really, really susceptible to electric forces and to magnetic forces. Now, that said, I want you to think of an electron, we'll place it right here, that experiences an electric field that points up like this, and a magnetic field that, say, points out towards us. Okay? So, here's our electric field E. Here's our magnetic field B. We're using the same coordinate system here, where this would be X, this would be Y, and this would be in the direction of Z. Now, this is an electron, which means that if you look at its charge, it's negative. And we're going to assume for the moment that this thing is at rest. So what happens is as this ray of light hits this material, if this thing is at rest, the magnetic field isn't really going to do anything to it. Okay, because we know the magnetic force requires velocity. Okay, I'm just going to write the magnitude like this. Okay, however, if you look at the electric force, it only depends upon the charge and the electric field. So what's going to happen is this. The light ray hits, the electric field here acts on this electron to exert a force through this right here. Now, since this is a negative charge, the force is not along E, but against E. It's in the opposite direction. So right here, and I'll do this in a different color. What looks interesting over here? We'll use purple. So here would be the direction of the electric force. And remember, it's this way because we're dealing with a negative charge. So the electric force would be up if it were positive, but here it's the electrons that are very mobile, so it's down. Now, so what that means is that you've created a velocity down like this, and now you've given something for the magnetic field to work on. Looking at this, though, the angle between B and V is 90 degrees, which means that we can use a very easy right-hand rule to determine direction. If I put my fingers in the direction of V and I close them towards B, my thumb says this way. However, sitting in the front, we have a negative charge, which means that the force that the magnetic field is going to exert is going to be this way or straight down the Z-axis. You see, it turns out that what is exerting the force on this thing and trying to push it to the right, due to light hitting it, is the magnetic force. So this right here would be the direction of the magnetic force this way. So let's talk about the relationships between these forces and between each other. We know, from a magnitude standpoint, to be clear, that in the x direction, specifically the negative x direction, but like I said, we're just looking at magnitudes, the magnitude of the force along the x direction is going to be Q times E, because that's the electric force. Now Q here is just the charge of the electron E. E is going to be whatever the magnitude of our electric field is at this point in space. In the Z direction, though, we have the actual magnetic force, which is Q, that is E, V times B. Now, we also know through the Poynting vector and through the energy that's trapped inside the electric field and the energy that's trapped inside the magnetic field that there is a relationship between E and B that looks like this. The electric field is equal to C times B. So what I'm going to do is to rewrite this in terms of this, noting the fact that B is equal to E over C. So if I put that in here, I have E V times the electric field over C. Now I'm going to clean this up just a little bit. This is V over C times E times the charge of the electron. And look at this right here. This right here is the same thing as the magnitude of the force in the x direction. So what that says is that the force that this thing experiences due to this beam of light along the z direction, which is going to try to push it to the right, is equal to V over C times the force in the x direction. Now, the thing that's doing very real motion here, that's having work done to it, is the electron. You can move the electron up and down, but you're not going to really move it into the material like this. So when you look at the work that's being done, the work that's being done is primarily being done by the electrical force, the X force. Okay? Now, so let's talk about power. Now, if you remember, power is a change in energy over time. Okay? We can also write power as the force that's doing work dotted with the velocity. Now here, the force that's doing work would be the electrical force, and V would be the velocity of the electron. So these would be in the same direction, looking at this right here, which means that this would just be the same thing as F sub x times V. And if I look over here at this relationship between the magnetic force in the z direction and the electrical force that's in the x direction, I have F of x, or F sub x times V. This is the power divided by C. So, the force that this thing is going to experience along the z direction, trying to push it to the right, is equal to the power that's trapped inside the light over the speed of light. Now, we're not done yet, because we know from our discussion in University Physics 1 that talking about forces at a single point is less realistic than talking about forces distributed over an area. So now I want to think of this thing as a wave, which is going to come in and is going to impact a big area. Okay? So maybe the area is right here. Maybe this is the area of impact right there, like that. Now, here, the force that's exerted over that area would be what we would think of as the pressure. This is the radiation pressure. Now, on the right-hand side, you would have P over area times C. And power over area is intensity. So what that means is that in this case, the pressure that's exerted by the light on this object, on a black body, would be the intensity of that light divided by the speed of light. Now this is for a black body. It turns out that when you have a perfect reflector, instead of that energy being completely absorbed, what happens is your light bounces off at the speed of light, which is the same speed that it came in at, which means that it actually deposits twice the amount of energy as a consequence of the reflection. So for a reflector, that would be 2 times I divided by C. A reflector here, this would be 100% reflection. And a black body, like I said, is defined as 100% absorption. Now, I'm going to subscript these pressures as B and R for radiation pressure on a black body and radiation pressure on a reflector. But these are them right here. Now, I'm not going to go very far into the derivation, except to point out the fact that you can take and you can look at the force that's being exerted on this thing, which is power over the speed of light, and you can look at the definition of power. Now, power is again d energy, d time. And you can look at the definition of force. Here, the force you can think of as the derivative of your momentum with respect to time. And I want to be very clear that this P right here and this P right here are not the same. Okay, and in fact, why don't I call it big M for momentum? And you can equate these. So when you do that on the left-hand side, you would have d momentum over time. On the right-hand side, you would have 1 over c times d energy over time. If you cancel the times out, what this tells you is that your momentum, m, really is just equal to the energy in your light over the speed of light. So, this is a very unusual example, and the reason why it's unusual is because light itself is a combination of electric and magnetic fields. It's not made out of matter, which means it has no mass. Previous definitions of momentum require a mass and a velocity, but here we have the ability to transfer momentum into something without carrying mass with it. All it does is depend upon energy. So let's examine this in the context of a problem. Here we have a ship using a photon drive. It's launched from Earth. We're going to assume that it starts from rest. The mass of the ship is about 5 times 10 to the 7th kilograms. And the drive emitter is a flat disk. It has a radius of 100 meters. Now what I'd like to know is what the intensity and the temperature of the disk would need to be in order to accelerate the rocket at about 2/10 of the acceleration due to gravity that we experience here on the Earth. And at that rate, I'd like to know how long it would take for the rocket to get to Mars and to Neptune. Now, we're not going to assume that it turns around and it slows down to get to Mars. We're just passing Mars. And then we'll pass Neptune as well. I'd also like to know how long it would take for the rocket to accelerate at this rate to reach 0.1 c, basically 10% the speed of light. Now, the reason why it's this and not 2% or 20% or 50% or even the speed of light is because after about 10% the speed of light, relativistic effects take over, and all bets are off. Things change, the equations change, which if you're interested in things like that, you can take a modern physics course and then go into great detail about things like that. And I'd like to know that at 10% the speed of light, how long would it take for this star to reach the nearest star system, which is Alpha Centauri? Now, in order to do this problem, we're going to need some additional information above and beyond what we've been given here. Let's just write down what we have. We know the mass of our rocket is about 5.0 times 10 to the 7th kilograms. We know the radius of our disk that's emitting the light, that's pushing us, is 100 meters. We also know that we're trying to get to an acceleration of 0.2 g. That would be 0.2 times 9.8 meters per second squared, which is, let's see here, 0.2 times 9.8, about 1.96 meters per second squared. Now, let's talk about distances. we're going to assume that we're going in a straight line from Earth to Mars and then to Neptune. Now, obviously, that's not the case in reality. These things are moving, as they go around in their orbits around the Earth or around the Sun. Um, it's a very complicated system. You have the gravitational attraction of the things that we pass along the way that can alter stuff. But we're just sort of back of the envelope calculating this. To that note, the Earth itself, if you look at the distance the Earth is away from the Sun, we say that it is 1 AU. That's the definition. 1 AU is 1.5 times 10 to the 11th meters. Now, in terms of AU, the distance from the Sun to Mars is 1.52 AU. The distance from the Sun to Neptune is about 30.1 AU. AU, like I said, is a unit of distance that we use when we look at the size of solar systems. It's much like a foot in that scale. As you can see, things fit very well into that length. And if you look at the distance to Alpha Centauri, well, that's better measured in something called a light year, which would be about 4.367 light years. And that's because it's a tremendous distance. Just from a perspective standpoint, this ends up being about 276,173.78 AU. So, we have now right here a conversion between AU and meters. If I were to convert this right here to meters, which I'll go ahead and do, 1.52 times 1.5 times 10, times 10 to the 11th. This ends up being 2.28 times 10 to the 11th meters. This right here ends up being 4.515 times 10 to the 12th meters. And this right here ends up being, let's see here, times 10 to the 11th, about a 4.14 times 10 to the 16th meters. Okay. Now, we're starting to get into the territory of exponents losing meaning. So why don't we attach a little bit of meaning to this? All right. So what I'd like to do is to call the distance from the Earth to the Sun 1 foot. Okay. Since most of the people that are taking this class or watching this video are from the United States, or you're familiar with feet. That said, on a scale where the distance of the Earth from the Earth to the Sun is 1 foot, noting the fact that there are 5,280 feet in 1 mile, this right here, this distance, let me just put it in here, 5,280. This is the equivalent of 52 miles on a scale where the distance from the Earth to the Sun is 1 foot. And that's the nearest star to us other than the Sun. So that should give you some perspective. 4.367 light years to the nearest star. Our galaxy from edge to edge is about 100,000 of these. We are, let's see, somewhere in the vicinity of about, this is off the top of my head, something like a quarter of that distance away from the center of our galaxy. So about 25,000 light years. So you're talking about tremendous distances here. Really, they lose meaning, which is the reason why when we talk about big numbers, we say that they're astronomical. It's astronomy. So we want to know how long it would take for the rocket to accelerate to 0.1 c. So we have another velocity here. I'll call this v sub c. 0.1 c is zero point 0.1 times 3 times 10 to the 8th meters per second, which would be 3 times 10 to the 7th meters per second. Okay, so thankfully what we have here is a constant acceleration. And so this is really just 1D kinematics above and beyond answering part A. So to that note, here's our drive plate. It's a disc like this that has a radius, something like this. The radius here of our disc, as given to us, is 100 meters. And basically what we're going to do is we're going to heat this thing up so hot, we're going to pretend it's a black body to begin with, which means that, it emits, all wavelengths of light. It doesn't absorb anything. Well, it does absorb everything that falls onto it, obviously, but it's just emitting everything. There's no reflection going on. So, so what this means is that if you were to look at the pressure that it is exerting to push us, that would be the same thing, basically, as I over C. So there's no reflection going on. Okay. Now this is pressure. Pressure is force over area. Okay. So so here, we want to know what would be required to give us an acceleration of 0.2 g. Well, force, conveniently enough, is m times g. If you sort of solve for things here, I over c would be equal to m, not g, but m times a over capital A. And we're looking for I. So I is going to be m times a times c divided by the area. Or m times a times c divided by pi times the radius squared, since it's a disk. So for part A, we want to know what this intensity is. We want to know what temperature this would correlate to. So, this is part A right here. So what's the intensity? The intensity here, the mass of my ship is 5.0 times 10 to the 7th kilograms. The acceleration that we're looking for is 1.96 meters per second square. C is the speed of light. That's 3 times 10 to the 8th meters per second. And then we're dividing that by the area. The area here is pi times r squared. R is 100 meters. Okay. So let's see what we have. So let's see here. 5 times 10 to the 7th times 1.96 times 3 times 10 to the 8th. Then we're going to divide that by pi times 100 squared. And I get an intensity of 9.36 times 10 to the 11th watts per meter squared. Okay. So this is the intensity. How does this correlate to temperature? Well, again, this is a black body. And if you go back and you look at our discussion of thermodynamics a long time ago, we talked about heat transport. And one of the equations that we talked about with respect to heat transport was the Stefan-Boltzmann law. Now, the Stefan-Boltzmann law says the following. The intensity of radiation that something puts out is equal to sigma, which is your Stefan-Boltzmann constant, times epsilon naught, or actually times epsilon, times temperature to the 4th. Okay. Now, epsilon, remember, is not the permittivity of free space. It is basically your emissivity. It tells you, how good of a radiator and an absorber your thing is. And with a black body, emissivities are 1. Okay. So to get our temperature here, it's really just the intensity of light divided by sigma raised to the quarter power, or the intensity of light, which is 9.36 times 10 to the 11th watts per square meter, divided by the Stefan-Boltzmann constant, which, if you look that up, let me get my notes here. It is 5.67 times 10 to the minus eighth watts per meter squared Kelvin to the fourth. And then you have to raise that to the quarter power. So let's see what you get here. You take that, you divide it by 5.67 times 10 to the minus eighth. And then raise that to the quarter power. You get 63,700 Kelvin about. Okay. Now, just for reference, the surface temperature of the sun is about 5,800 Kelvin. So this is incredibly hot. Nonetheless, it's what's required. So you would need some sort of material that would be able to withstand temperatures like this and still remain solid. So you'd be looking at something esoteric. Now, that said, there you go. Here's our intensity. And here is our temperature. Now, thankfully, parts B and C are actually pretty easy. And that's because, again, we're dealing with one-dimensional motion. So we know what our acceleration is. Our acceleration is, 1.96 meters per second squared. So here it's just simple kinematics. We assume that we're, leaving the Earth with an initial velocity of 0, like I had said earlier. So here, delta r, which would be the distance in a straight line from, the Earth, would be 1/2 at squared plus v naught t. It's just simple 1D kinematics with a constant acceleration. Now that's gone because our initial velocity is 0. So if we want to know how long it takes to get to Mars, from the Earth, what we would need to know would be the difference in distance between Mars and the Earth. So that would be 2 times delta r divided by a. Now, that's the square root of 2 times. Now, delta r is going to be Mars, where you end up, minus the Earth, which is where you start. This is Mars, and this is the Earth, right here. So it's going to be 2.28 times 10 to the 11th meters minus 1.5 times 10 to the 11th meters divided by the acceleration, which is 1.96 meters per second squared. Okay. So how long does this take? Let's see here. Square root of 2 times 2.28 to the 11th. And then divide that by 1.96. I get 282,120 seconds. Now, if I were to divide this by 3,600, that is 78 hours. You divide that by 24, and that's a trip from here to Mars in a straight line in about 3.3 days. So, drives like this are ideal because you're not having to carry what we call reaction mass. If you remember University Physics 1 and conversations about conservation of momentum, we know that conventional rockets heat up material to the point to where when it escapes a bell at the bottom of the rocket, it leaves at an incredible speed, but it's the exchange in momentum between that material and the rocket that causes the rocket to lift off. So to get the rocket to move, you have to eject material, which means you have to carry your fuel with you, and you have a limited amount of fuel. Here, the fuel would be in the source of whatever reactor you have on this ship. This is a tremendous amount of temperature, so you'd have to have one heck of a reactor. It would be a very nuclear reactor, potentially even antimatter, which would easily give you enough energy to do this sort of thing. Now, that said, let's talk about Neptune. So for Neptune, the calculation is identical. The difference here is your ending point. Your ending point here was, Mars, which is 2.28 times 10 to the 11th meters. Here, your ending point is going to be, where Neptune is, which is 4.515 times 10 to the 12th meters. Excuse me. So here you're looking at 2 times, what was that, 4.515 times 10 to the 12th meters minus where we start off, which is the Earth. And then, divided by our acceleration. 1.96 meters per second squared. So what do you get when you do this? Well, let's see here. Let's see. I get 2,110,469 seconds. Which, if you divide that again by 3,600, and then divide that by 24 days. So with something like this, the outer planets like Neptune are within incredibly easy reach. Less than a month to get out there. When now a conventional mission, because you can't carry your fuel with you, it just takes too much. It's just too much weight. It uses gravitational assist from planets and very, very complicated paths to get out to the outer planets. You're looking at missions that are on the order of years just to get to one of these planets. Here it's less than a month. Now, and I guess this really isn't C. This is B. Part B, I guess. C, though. C has us accelerating up to 0.1 C and then basically coasting. So what I'd like to know basically at the beginning is how far we would need to travel to get to that speed, and then how long. And the reason why I need to know how far is because I need to subtract that from our original distance. So to get to 0.1 C, what I propose we do is to use this equation right here. Super easy. Initial velocity is that. Delta R is going to be our final velocity squared divided by 2 times A. Our acceleration was 1.96. So how far is this? 3 times 10 to the 7th squared divided by 2 times 1.96 meters. So you're looking at 2.29 times 10 to the 14th. Or actually, better yet, 2.30 times 10 to the 14th meters. So you compare that to, the distance that we're going, which is substantially greater than that. We're getting there. So how long does this take? Again, we're starting off at rust. From the Earth, we're going to Alpha Centauri now. It's the same equation. Our ending point is here. Our starting point is here, the Earth. And our acceleration is just as before, 1.96 meters per second squared. So, square root of 2 times, we have 2.30 times 10 to the 14th minus 1.5 times 10 to the 11th. Then we're dividing that by 1.96. And that gives me something like 15,314,725 seconds. If I divide this again by 3,600, and then I divide this again by 24, this is 177 days. Okay. Now, knowing that, and knowing how far we have to go overall, let's talk about the remaining distance. The remaining distance would be the distance we travel to get up to that speed, taken away from this distance right here, 4.4 times 10 to the 16th. So the total distance we have to travel here, delta r, would be 4.4 times 10 to the 16th meters, which is the distance from the Earth to Alpha Centauri, minus this 2.30 times 10 to the 14th meters, which, as you can see, is sitting out somewhere around, like the second decimal place, basically. So when you do this difference right here, it's about 4.377 times 10 to the 16th meters that we have to traverse. So, it's the same thing. We're coasting, though, which means that delta r, which would normally be 1/2 AT squared plus V naught T, is now this right here. And our V naught is 3 times 10 to the 7th meters per second, because that's our speed. So this should take no time at all, right? Because we're traveling very fast, and, comparatively speaking, we don't have very far to go, do we? So let's see how long this takes. We're going to divide this by 3 times 10 to the 7th. I get 1.459 times 10 to the 3, 6, 7, 8, 9 ninth seconds. I'm going to divide this by 3,600. I'm going to divide that by 24. That's how many days. Incidentally, 16,886 days approximately, plus the 177. And now let's divide this by 365. Altogether, close to 50 years. That's to the nearest star, traveling at a substantial percentage of the speed of light. One that would need the introduction of relativistic effects to go beyond it. Almost 50 years to the nearest star. So, again, pretty cool little example. Now, where do you see realistic applications of radiation pressure and things like that? Well, we can look at our own solar system to see where radiation pressure is at work. Back when the solar system was initially condensed out of a solar nebula, there was a lot of dust and gas and stuff sitting around. But it's not there any longer. And the reason why is because the light from the sun exerted pressure on it and actually pushed it out into interstellar space. It turns out that the region between stars is actually filled with material. Now, when I say filled, we're talking about 3 or 4 particles possibly per cubic meter. But still, over light years and light years of distances, over enormous volumes, that adds up to a substantial amount of material. And a lot of that is a consequence of the light from stars pushing out material within their own solar systems. Now, um, that's it. That's the end of our discussion about the electromagnetic wave, about electricity and magnetism, and the end of University Physics 2.